All right. So for those of you who don't know me, I know a lot of you guys are back again for multiple times. Those of you who keep coming back to listen to me, I certainly appreciate that. So my name being Rob Ellis, I am in the technical side of things here for FIA. FIA being manufacturer's rep for several different companies. We resolve around the heating water industry, whether it's potable, whether it's, boiler heating, any of those sort of things. So this is all kind of in our wheelhouse of what we do. And we'll just go ahead and kind of jump right in here. So domestic hot water considerations, what does that mean? Legitimately means what should you consider when you're talking about installing, sizing, designing, or replacing a domestic hot water system. First thing I want to start with, and these are always, it's that voodoo science. We might ask you for a water chemistry report, you might get one, and there's all kinds of things on there. And they're really awesome if you're a chemist, because you'll understand what they all are. But I want to touch on a few of them here, what they mean. And these are the ones that are the big impactors of basically your water system and how that's going to work. So, but this is basically what you're going to get for a water chemistry report. It's going to give you what your actual test results were on site. And then generally over there in the column, there's an EPA kind of standard. One of the things I found as I was going through, kind of learning about this and figuring out what all those numbers mean is sometimes the EPA standard, if there's no health risk to it, the EPA standard doesn't do much to talk about the piece of equipment or protecting your water piping or any of that. That's not what the EPA's job is. They're really looking at, is it a health risk? Well, in some cases like pH, it's not so much a health risk to you, but it could be water, the quality of the water, the taste. Conductivity is another thing where it can be the taste of the water, those sort of things. So it's kind of important to know the difference between, well, the EPA says it's okay, doesn't mean that it's actually okay for your heating equipment. If that makes sense there. Let's talk about a couple of things. So pH, we talk about pH all the time and what it is, but it's really, where we are we, alkaline? Are we acidic in our water? Are we neutral? In the heating side of things, the condensing boiler world, we probably are exposed a little more to pH because that's what we're talking about in our condensate neutralization kits. But it really talks about, so they got here, high pH, bitter taste to the water. That's when the EPA might say, hey, the customer's not going to be happy, the end user. And then you get buildup on your stuff. Low pH, now we can corrode and dissolve metals and other substances. What can make pH low? Most common in heating side applications, when we see low pH, that's really degraded glycol. Obviously, because we're talking potable water today, we don't see that. And most pHs is balanced really by the different water companies because they don't want high and low pH in their water pipes. So they do a pretty good job of monitoring where the pH level is. We generally like to be in that range of that 7 to 8.5, 7 to 9 maybe range is where we want to keep that pH. If we cross 9, we're going to start seeing buildup. Drop below 7, we're going to start to corrode and damage our pipes. So that's pH. Total dissolved solids, junk in your water. It's literally what it is. It is stuff that's floating around in our water. It's dissolved into the solution. So it is. So now here's the thing that's always a weird one. We all go out and get mineral water, right? Well, maybe not all of us, but people like to drink mineral water. And that's really what that is. And it kind of notes that it's not heavy metal contamination. So we're not looking at any of those sort of things that are really harmful, the arsenics, the lead, the iron. We're just looking at different, this could be zinc, this could be sand or dirt in the water even, any of that kind of stuff there. Now, what that really contributes to is, this corrosion and scale deposits. And you got a little picture right there at the bottom. We're up in the yellow area for the most part of the New England area. So it's not bad, it's not great, but it's, the thing about dissolved solids is when you heat water, those begin to precipitate out of solution. And then they're going to end up on the pipes in your water heating equipment, potentially in your tanks. Most of dissolved solids are actually easy to take out utilizing some sort of filtration system. Just a typical spun whole house type of filter. That's going to take care of your dissolved solids. All right. So that's what those are. And those are things that can just cause buildup. They generally dissolve solids, probably more detrimental to a tank type water heater because they're going to come out of solution. They're going to settle down onto the bottom of that tank and they're going to begin to build up and create an insulated barrier between your flame and your water. And that's going to reduce the efficiency of your water heater, can potentially get to the point of causing damage and failure to a water heater. So that's dissolved solids. Chlorides. Knows what chlorides is? It's salt. Salt makes water more corrosive. Of course, you know, road salt corrodes our cars. You know, salt is a corrosive mineral, and then it gets into that stainless steel doesn't like chlorides and copper doesn't like chlorides, and those are basically what we heat with. We use those two products as a general rule. Now here in New England, we have very high, or I shouldn't say very high, but we have a lot of chlorides in our water, which is also, how do you soften water? With salt, right? We got a water softener down there. We're going to use chlorides to soften our water. We're naturally softening the water here in New England, basically with the road salt, the runoff, and things like that. So for heating equipment, 150 parts per million, definitely want to have that salt content below where that is. So that dovetails our way right into hardness. And what is hardness? And interesting, I always thought that, well, everybody's got hard water. It's all I hear, talk about hard water, hard water, hard water, hard water, and you need to get a water softener. And then the reality is, in our area here, our water is soft. We're generally, in most places, in that too soft area. You may see this referred to as grains per gallon or milligrams per liter. It really depends on how it's termed. That 85.5 milligrams per liter works out to about 5 grains per gallon. And coming up, I've got another slide. It's got a little picture on there, and our whole area is in that too soft water area. So when water is too soft, a little note on there, well, here's what can happen. I am sucking the minerals out of the piping, within the system piping. I'm going to pick that up as I'm traveling through, as the water is moving through it. It's kind of going to leach those minerals out, and it's going to carry them with them. And that's kind of the thing that soft water does as it moves through and along. And water is an incredible corrosive material. I mean, it's what it's great at. Made the Grand Canyon, right? Worked its way through, wore its way down. And generally, what water is going to do is it used to do a good job of balancing itself as it moved through the water table. It was collecting minerals and it was doing that sort of thing, and it just got to its natural equilibrium. And then we get involved and we do all kinds of different things to our water, you know, depending on what's going on. Now, soft water is great for taking a shower. Your soap's going to lather up. It's going to do stuff like that. A whole lot better than hard water. But finding that middle ground is really important. And you notice it's a pretty small area on that chart where that water is at that right spot. Because all of a sudden I'm going to start crossing into scaling. And then I'm going to get to this point that I'm just going to be a disaster. So it's getting that water just right. And most of our water companies, you know, this is what they're doing. They are really monitoring what's going on and taking care of that. For guys that are on wells, there's nobody doing that for them. And that's sometimes why we see well water tends to be a little bit harder as it's coming up. It's not getting softened by the various things and that type of stuff. That's hardness. Conductivity. So this one's getting way out there in the world of science nerdiness, and let's do some Bill Nye experiments. So conductivity is really kind of the mineral content, if you will, of the water. And some of the mineral content in there actually can create this electrical current through different dissimilar metals with high conductivity in water And basically we get that galvanic corrosion or electrolysis. And then that's going to attack joints, solder, those sort of things. So it's going to get your solder joints. It's going to get all those type of things is really what's happening when we have that. What's a solution for conductivity? A filter, because again, you're just filtering out minerals and you're not trying to get any of the, we're not trying to pull out lead and those sort of things. And back to the soft water, that's what really created the lead issue, is the soft water moving through lead pipes, leaching lead into the water, and then making its way into the house. So that's how that was picking it up. And we all understand why we can't have lead pipes anymore. We can't have lead fittings because the water was pulling the lead out of the fittings in the pipe. It's no different. We're not pulling lead out. People don't care because it's not a health issue, but it's certainly a health issue for our heating equipment. So recirculation pumps. And while this seems like kind of a meandering through the woods, it's all going to tie in here. So if I pass my water through my heater and I heat it up and I do its thing and off it goes into the system, yeah, I'm going to chase around some of the issues, the hard water, pH, that sort of stuff. But this is where soft water can really come into play. Now that soft water, as I recirculate it through my building, what's it doing? It's picking up all the minerals throughout the building. And then it comes back and it deposits them in my water heating equipment. And it puts them on the surface of that. And that begins to cause that buildup on those surfaces and can lead to issues. What makes it worse, and I've got this example down there at the bottom, which is an awesome example because it's so ridiculously oversized compared to what we were going into, that to be able to say, hey, for $1,000 we saved 4,000, and we save 4,000 every single year, and they're now 5 years in to those new pumps. I mean, that's a ridiculous example, but it happens. When in reality, we went to this little 1.6 horsepower ECM pump that I think at the end of the day, it's circulating something like 5 gallons a minute through the building, as opposed to we were somewhere around 75 gallons a minute that they were circulating through there. So there's a little chart there. And when I send out the link sometime between now and when I send it out, so I'm not going to commit to an actual time, I'm still a little behind on those. There's going to be an article in there that was written by FIA's own George Carey. And it literally talks about sizing these domestic hot water pumps and really how small the pump needs to be. But there's two parts to that conversation of that pump being too big. One is the big pump costs us more dollars to run. The other one is if I have soft water and I'm running around and I'm picking up minerals, the more water I circulate, the more minerals I'm going to bring back, and I'm going to deposit into my heating equipment. Slow your pumps down, increase your overall electrical efficiency, do everybody a favor and use less electricity, right? But in reality, let's protect our equipment by not moving so much water through theirs. And there's a ton of these little recirc filters. We did a project out in Westfield with these tiny, like 1/3 horsepower ECM pumps for 24 apartments. Circulated around just fine, no issues. It handled the load because all we need to do is keep it warm at the tap. We're not trying to fill the pipe or fill the tap or fill your shower with that pump. All we want to do is circulate that water around and keep it warm at your tap. So that's why we don't need those big pumps. The big pumps can be hazardous. Just adding more velocity, more pressure, all sorts of things within our system. So that leads me to recirculation filters. Seems ridiculous, doesn't it? So the recirculation filter is installed on the recirculation line when we come back to the water heater. So the picture you see there on your left-hand side there, that is 2 recirculation filters that were installed. It's one I should say it's one because they stack 2. This is up at UMass Lowell. And UMass Lowell and some areas around there were 2 sites. We're doing a very good job of going through water heaters. eating up heat exchangers. So this was the solution, which at the time, the first time we did it, sounded absolutely ridiculous. How is that going to solve my problem? So in that picture, those are filters that have been installed for 2 weeks in a hot water recirculation line. I mean, so think about that. And the pump actually on those was a 007. So we're really not talking that we had a ton of flow coming back there, but this is what we went from. There's the brand new ones and the ones that have been installed for 2 weeks. On the right hand side, you see the cartridge housing. When you're into this, just beware that your typical whole house filter might not be able to handle the warmer temperatures, the hotter temperatures. Potentially you're going to see 110, 120 degree water coming back to that recirc filter. So we want to size it that way. In the red at the bottom, what you have there is a notice in a manufacturer's manual, okay, now on a water heater. And in there, they basically said, now these notes are specific to that 5 grains per gallon. And what they're saying is, well, flush and clean your existing stuff first, depending on what you're connecting to. Obviously inspect everything, that's simple. Y strainers are always a good idea. That's going to get me my big chunky sand, and it does collect some of the zinc, and it'll collect some of that stuff. It's going to get the big stuff. Limit that run time of your hot water recirculation filter, which is tough. I know that a lot of the mixing valves require that 24-hour a day circulation. So if you can't shut it off on temperature, maybe you can on time in the overnight hours, or just slow the flow down. If I take the flow in a domestic hot water recirculation system from, let's call it 15 gallons a minute, which we see all the time in those 1.5, 2, 3 horsepower, 3-piece recirc pumps that are out there, and I could drop it down to the 2 or 3 gallons a minute that it should be. If I eliminate 12 gallons a minute of flow, that's literally like shutting off that pump for several hours of the day, because I'm reducing the amount that I'm flowing through there. So it kind of helps to balance it out. And then the next thing is filter it down to a level of 10 microns. I didn't put the picture in here, but that filter there on the right hand side is actually installed with gauges, and we didn't see a substantial pressure drop in those gauges across that filter. So it wasn't really creating some issues for us in there. Now, they have an appropriately sized recirc pump, but if we had one of those big recirc pumps, we might see it as we were trying to move high velocity through one of those filters. So water pressure. So, real quick, let me get this here. So Nick's asking location of that recirc filter. It's actually a pretty good question. So in this case, and it's whether it should be before or after the recirc pump, will that make a difference? And where it should be. So we want to be on the return coming back into basically the mechanical room. He's asking about whether it should be the return to the water heater, but get it on that common return. Sometimes we split off to run some through the water heater, some through the tanks. Get it there before we split off. So as soon as we get back into the mechanical room, throw that filter on. And then his next question really being before or after the recirc pump, will it make a difference? And it doesn't make a difference there where it's going to be in the system. So we're not particularly protecting the pump from anything, so we don't need to put it upstream of the pump. In a lot of cases, it's put it in where it fits. We do a lot of that when it comes to inserting one of these back into a system. All right, so get back in here, and so let's talk about water pressure. So this is actually at my own house. I have some pretty bad water hammer at my house, and again, another thing I've been looking into. So, and the cause of these pressures are generally for our water heating equipment. We want to keep that like 50, 60 PSI. That's that area, really no more than that. So as the infrastructure or as the population density has been increasing, we need more water. People are putting fancier bathrooms in. We're building more houses. You know, whatever it is we're doing. There's a, I think, 150 unit apartment building going in here in my town. But we can't dig up the pipes and make bigger pipes. So the only thing we can do is increase that pressure. And so it's bigger pumps that can pump more. Crank that pressure up, very similar to what we will see the electric company does. You know, the electric company wants to crank the voltage out of the transformers right as much as you can. So when we all turn our air conditioners on in the summer, they're not coming out to take care of it. So it's a very similar scenario there. So what happens though is during the day, everybody's using their hot water, everybody's doing their thing, washing their hair, washing the cars, doing whatever. That's daytime usage. We all go to bed, some of us. And now we don't have that draw on it, and we're seeing pressure increase. So in this case, my house went from 80, which was the standard, and you know, used the tattletale gauge, and spiked to 120. So that's 120 pounds of pressure I am putting into my system at times. That's on my heating equipment. It's on my tank. It's all of that there. We're increasing that system pressure. And those are all going to have impacts. Where's that hammer come from? Now I've got this pressure. I've got these solenoid valves. These solenoid valves are slamming shut, and I have a backflow preventer at the street. There's nowhere for this to go. Now I start creating extra banging and hammering within the pipes. On the side here, this is a pressure reducing valve. This is actually the one that's going into my house, which, you know, so I've lived in my house for 8 years, never gotten around to doing it until, you know, I started putting this thing together. I said, oh, maybe I should start doing that. So what does a pressure reducing valve cost? Less than $100. So it's going to be that, couple of fittings. Of course, I made the mistake of having my buddy Mike come over to do it for me. And Mike does everything. He'd probably build a nuclear power plant in my basement. I think I'm getting 2 gauges and all sorts of stuff getting put on there. But you know, that's generally an easy installation. 3/4 inch, thread in your fittings. You know, press adapters or whatever you're using, and put it right in there. Let's. There we go. All right. So expansion. So water expands when heated, which never used to be an issue until backflow preventers came into play, and we started putting those on. And now as our water expands, I can't go back out of the system. I can't compress the water. So the only thing that begins to happen is my piping system or my tank or whatever is going to begin to expand. And then when I use the water, what happens? It contracts. And it's going to expand and contract again. Now, residentially, 40-gallon, you know, tank or a 40-gallon indirect, maybe 3/4 of a gallon expansion. It's not a ton. Now let's step that to a commercial application. And I've got 800 gallons of storage. Now I've got 20 gallons of expansion. Where does that go? 20 gallons of water is a lot of volume. So that's where we get into, you know, expansion tanks become important, getting those installed in the system so they can accept that expansion. And this little illustration on the side there, little hokey, but it's really showing what that expansion can do in those tanks. Whether I've got that, you know, that center tube through there for my water heater, and I can begin to crush that. I'm pushing down on the bottom of my tank, up on the top of my tank. So all these various things, does my relief valve start to trickle? What if I'm building my pressure to 125 PSI at night and I'm expanding within my tank? You know, so we could be going out there saying, oh, I got a bad relief valve. Well, what caused my bad relief valve? You know, all these things begin to kind of come together. Now let's just take a second here. Now we're just going to have the worst case scenario. Now let's say I've got high dissolved solids and I'm heating water in my tank type water heater, and those solids come out, they sit down there at the bottom, and I heat and cool them, and I turn them to concrete. And that's usually what kills that tank type water heater. Now I have this concrete bottom. I'm certainly not going to get any deflection or expansion and absorption there. So now I've got a nice hard bottom, and now I'm putting more and more pressure on my tank, creating those failures of a tank type water heater. So just more things to deal with. Here's a quick chart. And again, you guys are going to get this afterwards, but it's just a real quick sizing chart. And as you can see, for most stuff, that 2.2 gallons of acceptance is really what you're looking for. It's like a PT5 expansion tank, just a little guy that handles it residentially. And then it obviously will increase in size as your stored capacity increases as well. All right. Anti-scale filters. So these are kind of a unique product and have a very specific use. And what these are really good for is that one time through the system, a tankless water heater or a combi. Why it's good for that is it has the ability to, as this, the stuff that's going to scale up in your water heater, as it begins to come through, it actually does some sort of, and believe me, if I could describe the chemical, or electrochemical process that happens in there, I would have invented it. I would not be sitting here in my basically spare bedroom talking to you guys this morning. I'd probably be on my own island somewhere. But it's a pretty cool chemistry thing that goes on, and as it goes through, it changes it. They become inactive, and they'll pass right through your tankless water heater or your combi, and off they go. So, I've even asked the question, well, why wouldn't we do this on a tank type water heater? Why wouldn't we do it on our split systems? Because you don't get rid of it. It stays in the system in those. It ends up in the tank. It does all these things. So it really defeats the purpose. This type of product is very specific to tankless and combi style units. Good for hard water. But as you look at the, kind of the picture we've got there, we're up in this soft water area. And I didn't have enough room to put the whole explanation chart, but this light gray area is that extremely soft water area. So that's us. But you could be, if you're pulling off of a well, you could certainly have some hard water. All right. So what happens to water when heated? That's why you guys came, right? And I've given you all this horror stories of water's terrible. You should stop drinking it and stop taking showers, and really the world will be perfect. So water does get more corrosive as we heat it. And it's all this water chemistry in that's going to come into play. So from 60 to 140 degrees, we're quadrupling the rate of corrosion, if you will, that's created. This galvanic corrosion increases as the water temperature goes up, and the minerals come out of solution. Once we go above 140 degrees, we're going to double our corrosion effects every 20 degrees of storage. So 140 is really that area where you want to stay away from if you can. Really, the challenge is for some of the bacterial things, they want us to be above 140 degrees. So it becomes this balance of really where we're looking and what we're doing on there. But just keep that in mind. The hotter you're heating your water, the more corrosive, the more of these effects that you're going to have. All right. So all the bad things. How much hot water do you need? The answer is it depends, right? Could have two houses side by side that are going to have completely different domestic hot water characteristics. Could have 2 3-bedroom, 2-bath ranches, one husband, wife, young child. Not a lot of usage. 15 years down the road, husband, wife, 3 kids. We've definitely increased the usage within there. So it's always looking at what's there, what's going on, what are the fixtures. From time to time, we'll get a request, somebody sizing, hey, I got 2 bathrooms. We got a tub and washer and dryer. And then it's 2 bathrooms with fancy showers drawing 20 gallons a minute and an 80-gallon soaking tub. That's a pretty substantial domestic hot water load. So it's getting a little more information as we go. We talk about restaurants. So restaurants tend to have a continuous load and then a dump load. When we look at restaurants, it's how many of the slop sinks and the wash sinks and the prep sinks do they have? Because generally what they do is they'll go and fill 3 of these 18-gallon sinks simultaneously with the hottest water they can dump into it, use them, drain them all at the same time, and then fill them all again. Well, I'm rapidly using 60 to 80 gallons. Right now I'm going to fill those things and can probably fill those things in, 7 to 10 minutes because we're doing it in 3 sinks. That's a big dump load that is that's going on your system. So a dump load requires me to have what? Storage. Got to have storage to handle it, and then I can go and recover it. One of the greatest examples of that is the Zamboni, which until I got into this industry, I had no idea that we filled Zambonis with hot water. So if you didn't know that, you're welcome for that tidbit of information. But the Zamboni would run on the ice. It would come back. They would fill the tank. They'd, 150, 120, 150 gallons, dump it into there. Off they would go. Now, while it was out doing its thing, you could recover your tank that you're going to fill your Zamboni with. Where they get into trouble is, end of the day, dump the tank, fill the Zamboni, people go and take showers. Now you've got a couple of loads to put into consideration there. So what are our first hour needs of the system? First hour is basing it on what is my storage and dump capacity coupled with my continuous recovery of my water heater. Now, that sounds like that should be really easy. And I'm going to show you a slide here in just a minute. It's going to explain why that's not so easy to figure out. But again, first hour needs. Notice in there, call out a business hotel. So we'll talk about the West and South Boston, right next to the BCEC Convention Center. When they have conventions and business stuff going on, people are getting up in the morning in most every room, taking a shower, getting ready for the day. We'll go about 30 miles north up into Danvers to I think it's the Doubletree that has Cocoa Key Resort in it. Now, my hotel rooms are full of families and kids. We're not getting up in the morning, early, all hitting the shower doing that, but you can get into scenarios where everybody's coming back at the end of the day and hitting the shower. So just where do those balance? And again, that's more information that we need when we go to size a domestic hot water system. Residential demand. So this is a typical 3-bedroom, 1-bath house. 2.5 gallon a minute shower head, no problem. That tub faucet, that can jump up to bite you, 5 to 7 gallons a minute. Bath, kitchen faucet, washing machine, dishwasher. In this scenario, sometimes we miss that tub, especially if we start going to an instantaneous type system. That we get an instantaneous type system that might give me 3.5, 4.5 gallons a minute, but it might not keep up with my tub demand. So important things to look at how people are using that. The other thing about residential things, and we run into, so in FIA's territory, we cover ski resorts and we cover beaches. Cover a lot of normal stuff too, but ski resorts and beaches have particular types of uses. If I go down to the Cape and I have a house on the Cape and I invite 15 friends to come down, we're going to go to the beach, we're going to have a party, we're going to do whatever. And at the end of the day, all 15 people come back to the house and take turns taking showers. I'm going to get a very long, continuous demand in those scenarios. So I have to be prepared for that. I can see the same thing up in a ski resort. So anywhere you've got a spot where, these kind of vacation spots, or we have that type of scenario, you look at the same thing if you have a hotel that specifically caters to weddings and have exactly the same thing. All the guests are going to go out, do their thing, and then they're going to come back, all take showers and get ready for the event. So always try and know, hey, what's the use of this building? That's going to give you a lot of inclination as to what's going on, what you do. How about a multifamily demand? So used to be we had to do everything by hand and calculate it out by hand and do that. And some of the boiler manufacturers, Lockheed included, some of the others put out these great charts with how to do the math. This many apartments, you're going to do this. Here's your diversity factor. If you got on early, you heard Tom Gaudette and I, Tom being an old type of boiler guy, I'm not going to call him old today, at least not in front of you guys, is a scenario where we also factored in our diversity factor, that assumption that everybody wasn't taking the shower at the same time. And so we were talking about, how many people are now, everybody's home all day. Are we seeing these heavy loads on some domestic hot water systems? Luckily, I haven't had any calls, so that's certainly a plus. But we're going to use, just an ASHRAE example of how to calculate this out, and then we're going to go look at online calculators. So I went to 3 different manufacturers' websites, and I put in the same information. These are the 3 answers that I got. Same information, same building. Now there's the peak demand, which is saying, hey, I think most of my people are going to use it within an hour, or it's a 3-hour demand. The reason I kind of put this up there is to show you that there's a little change can have a big impact on what you end up sizing your system to be. And then you can certainly end up short. If I use the ASHRAE sizing guideline there, 60 units, they figure, 8.5 gallons per hour per unit gives me 510 gallons per hour. So now my first example is I have BTU in storage. Now I have gallons per hour. Where do I take that? If you want to do it, you're going to take the number of gallons times the weight of the water times the degree of rise that you're looking for. In this case, we're looking at a 40 to 140 rise in temperature. And I did this just so I could match the calculations from those manufacturers' calculators. And this only gives me my BTUs. Those BTUs are assuming that I've got some storage with it. So that gets calculated out. And then you follow on with that is, do I want redundancy? What do I want? How do I want to size it? So I'm not trying to make it more difficult, but there is just a ton of stuff that goes into calculating a domestic hot water system and what you're going to select for equipment in there. Now this here. So I hear this conversation a lot, that brand X is more efficient than brand Y at heating the water. And just be cautious, when those things get made. BTUs to heat water are BTUs to heat water. End of the day, if I heat 100 gallons of water, I'm going to need the same amount of net BTUs no matter what piece of equipment I use. The difference is, how do I get to my net BTUs? My net BTUs that I'm going to now put into the water to raise that water temperature. If we look on kind of the surface of it, thermal efficiency is your big thing. If I took a 95% efficient tankless water heater and I took a 80% efficient tank type water heater, my difference is that efficiency. And that's the difference in how many gross inputted BTUs I'm going to use to get a net. So hopefully that makes sense right there. So when I'm talking about my flame, that's the difference. Gross, input, net output. And we're looking at burner efficiency right there. What else is going to impact me? Well, what am I now using to transfer the energy to the water? And that's kind of the next piece of that puzzle when we start talking about a system's efficiency. So we're going to start with, and not going to good, better, best. This is a tankless or a combi unit. I'm going to directly heat the water on demand. That's what I'm doing. So whatever my net BTUs are, burner efficiency to net, goes into my water. That's pretty simple, right? That's what I get. If I net out 95% efficiency from those BTUs into there, that's what I'm putting into the water. just some things to consider when we start talking about, tankless and combi units are, directly fired. That's where we see some of our scaling things. If you miss on a tankless, an instantaneous unit, its capacity is its capacity. It's gonna be sized by the temperature rise in gallons per minute. That's all it can do. So if we size it out and say, I'm getting 4.8 gallons a minute at a 77-degree temperature rise, it is what it is. If you need an 80-degree temperature rise, you're going to get less gallons per minute. If you need more gallons per minute, you will get less temperature rise. So hopefully, if I put 6 gallons a minute through it, I'm not going to get a 77-degree rise. That might work okay if I'm in Arizona and I got a warmer groundwater temperature. It might not be so hot if I'm up in Caribou, Maine. So again, just considerations to take into place. You can't turn the water temperature up any more than what it's going to give you in those. But they've got a lot of benefits. Low priced, space saving. If you've got a home that's not used all the time, there's no standby tank sitting there full of water, those sort of things. So again, pick what works in your application. Remember, when we talk about these, just the one thing that I see people get caught by are generally the tub spouts. So if you're gonna put one of these in, you got a tub in there, probably put a flow restrictor on it, so that you can't draw too much water through that unit. How about a tank type? Tank type's been around forever. Everybody's seen one. Hopefully everybody's at some point in time seen the really cool video of the guys blowing up the tank type water heater by plugging the relief valve, which is only good to mention because it's probably one of the coolest things to watch a tank type water heater launch itself into the atmosphere. But this is where I talked that first hour rating. So a 40-gallon tank, you would think that you would get to use all 40 gallons as your first hour, but you don't, because the minute you start to open that faucet and you pull that incoming cold water in, that is going to dilute the water in there. So in this case, and this is taken right from a manufacturer's ratings on it, 40-gallon tank, 40,000 BTU burner. That 40,000 BTU burner has a 41 gallon an hour recovery. But we only have 67 gallons of first hour. So where's my math, right? I got 40 gallons of stored hot water. I can make 41 gallons of stored hot water. Within an hour, I should get 81 gallons, but I don't because it dilutes. So in that case, I have a 67 gallon first hour rating. So those are important, numbers to know, especially residentially. Somebody goes and fills the tub. Now the thing's going to recover. How much do I have? Do I have enough to do that? So that's a tank type. Tank types are on everybody's shelf. You go buy one, put one in. If it fails, take it out. Go put another one in. How about a split system? So now we start to get into bigger ones. These have been around for years. And basically the concept here, the initial concept was when I heat my water in a tank, that tank type water heater, the stuff comes out of solution, those dissolved solids, and they end up in my tank. Most tanks heat from underneath. I'm going to insulate it. So if I went to a split system, my heating is going to take place in whatever's connected to my tank, whatever kind of water heater I have, whether it's a high efficiency or it's a standard efficiency. I'm going to heat the water as the solids come out of solution. I dump it into the tank. Those solids end up in the bottom of my tank, but I'm not heating from the bottom of my tank. So I'm not impacting the efficiency of my system. I'm not creating that insulative layer because I'm not heating and cooling those dissolved solids. I can actually drain them right off of the tank. You generally see two different looks to a split system. Right-hand side, we've got a water heater and a tank. Left-hand side, we have what looks like a tank type, but there's a water heater unit, direct fired water heater unit sitting on top of the storage tank. And that's to make a simpler package. And that's how that works. Those are both split systems. The advantage to the one on the right-hand side is being able to configure it for redundancy and larger loads. I could put 2 or 3 heaters together and 4 tanks whatever my application is going to be, it certainly gives me some additional solutions. Um, when we talk about multiple units, and I have the two there kind of side by side, right? The tank style model, if you will, if I put two together, I still use both at the same time because my flow is, basically reverse return through the two units. I'm always going to flow water through both. When I go to the other side, those heaters aren't kind of directly in the path, if you will, to the faucet. So when I turn my water on, I draw through the tanks, and then the heaters will come on as needed. So I can stage my heating on. Gives me kind of an ability to handle larger loads and modulate down for smaller loads. It's kind of where that advantage is right there. Okay. And indirect. So indirect heating basically means I am heating some medium somewhere else, running it through a internal coil. So on the left there, see a cutaway of just a stainless steel indirect. So the tank would be filled with the potable water. Inside of that coil, we would be running our boiler water. So I'm doing some indirect heating. On the other side, that's a hot water generator. Those can be connected to steam. Those can be connected to, water heat, boilers, whatever you have. And then there's a tube bundle inside. We can get into some bigger loads. Sometimes we don't want to put a separate domestic hot water system in. So this is what we're going to use. Now, this is where we change a little bit that conversation of BTUs or BTUs, right? The BTUs are the BTUs. Getting to my net BTUs that I input into the water is the difference in efficiency. So in this case here, I'm going to connect it to, let's just say I'm going to connect it to a boiler, and I'm going to heat the water that's in the coil with a boiler. That's one heat transfer process, right? I'm going to directly fire into that water. When it comes out, now I'm going to transfer heat through that coil into the potable water. That's a second heat transfer process. So I am going to lose some BTUs along the way. So just, as you're sizing, keep that in mind as we start looking at, hey, where's our efficiency and what's more efficient? And the reason I don't spend a ton of time telling you what's more efficient is it's different. It depends on every single application. If I've got a heating system already up and running and I want to hook up some indirects to it, and I already run at 160, 170 degrees, that's a pretty easy solution because I'm not adding equipment. If I've got a big domestic hot water load and maybe I run a boiler plant for a condensed water loop at 60 degrees, 70 degrees, well, maybe a separate system is what I need. Sometimes these indirects work really good on applications where we have really bad water. We have some areas here with a lot of zinc in the water. Well, if I'm not heating that zinc on a heating surface, it's generally going to stay in an area where I can clean it off. I could go back in, flush those tanks, and clear out any sort of that buildup. Whereas if I put a direct fired unit in there, I'm not going to be able to clean that up. It's going to build up on my heat exchanger, potentially have a failure. So like I said, there's no one size fits all domestic hot water solution. How about questions?